Hi, I'm Tom Beebekauser with Wetland Restoration and Training. We're going to be looking at how to build wetlands using the compacted clay liner technique. We use this technique when no groundwater enters the test holes that we dig, when we're not able to build a wetland using a groundwater dam, and when there's at least 4 foot of clay near the surface. You may wonder, does the technique work? Yes, it does. Look at this beautiful wetland behind me. We built this 17 years ago using the compacted clay liner technique. Now there's a lot to it, how to use this technique, but that's why we're doing this video, and I hope you enjoy the show. This is a natural wetland called Booth Pond. It's located on a mountain ridge in eastern Kentucky. The wetland is in a shallow basin where the texture of soil is high in clay and the clay is compacted. This is also a natural wetland that's found in a basin of compacted clay only on top of a sandstone ridge within the Danube National Forest. We call this Cliff Palace Pond. Carbon-14 dating shows that Cliff Palace Pond is over 10,000 years old. Wetlands built by humans can last a long time. This wetland was dug by hand over 2,000 years ago using the compacted clay liner technique. It's located at the Fort Ancient Earthworks and Nature Preserve near Oregonia, Ohio. You'll find 114 wetlands that were built using the compacted clay liner technique at Fort Ancient Earthworks. They're all located on a high ridge overlooking the Little Miami River. This wetland was built in Columbia, South Carolina in the 1700s by compacting clay in a basin. This small wetland formed in a pit that was dug by hand where iron ore was mined in the 1830s on the Danube National Forest in Kentucky. The basin is surrounded by clay, and the clay in the basin is compacted. Here's a wetland we built 20 years ago at the Southwestern Research Center near Portal, Arizona. We used the compacted clay liner technique. This drawing shows the many components of a wetland built using the compacted clay liner technique. Some people think that all you must do to make a wetland is to excavate a depression in the ground. This rarely works because plants will drain the water in the basin, their roots will penetrate the soil, the freeze and thaw action will crack the thin layer of compacted soil, and the periodic wetting and drying will also crack any clay that's present in the basin. This photo shows a puddle in a field on our farm after a heavy rain. The hole was dug by our dog. The water in the hole drains into the ground after a few days. This puddle also formed on our farm after a heavy rain. Our goats made the basin by wallowing on their backs in the dry soil. Within a few days, the water will soak into the ground because of the roots and the fissures in the soil. To build a wetland using the compacted clay liner technique, one must excavate a basin that is 24 inches deeper than the wetland you're planning to build, and then line the basin with thin layers of clay, each of which is compacted until the total thickness of clay is 24 inches or more. The hole you initially dig for the wetland should have nearly vertical sides that you can form a wedge of compacted clay that's at least 24 inches thick beneath the outer edge of the wetland being built. The soil used to line the wetland basin must contain at least 38% clay. This means that you must consistently be able to make thin ribbons of soil that are at least 2 inches long. The high clay content is important because it's not possible to compact soil that has a lower percentage of clay, which means that if you build the wetland using sandy loam or silt loam, the wetland will leak and it will fail to hold water as planned. You should dig 1 or more deep test holes in the area where you want to build a wetland to determine if the compacted clay liner technique can be used. It's a legal requirement that you call or go online to request a check for buried utilities before you dig. I'm continually amazed at where utilities have been buried in the ground, even in remote locations. This drawing shows where it's possible to build a wetland using the compacted clay liner technique. There's a layer of clay at least 48 inches thick near the surface, and no groundwater enters the deep test hole that we dig. The lowest cost way to build a wetland using the compacted clay liner technique is to build a wetland where clay is found near the surface. This deep test hole shows that there's a layer of clay that's at least 4 feet thick near the surface after removing the topsoil, which means there is enough clay to build a wetland at this location. Do not use the compacted clay liner technique if water enters the test holes you dig. Use the groundwater technique instead. It may be necessary to haul in clay with dump trucks if you want to build a wetland on a site where there is not at least 4 foot of clay near the surface. While this practice of transporting clay sounds reasonable, it's actually very difficult and very expensive to accomplish. If clay texture soil is not present or adjacent to the area where you want to build a wetland, one must find a source for the clay, pay someone to load it, and then haul it to your site using dump trucks. Before the clay is delivered, you should prepare the site by excavating the basin and spreading the soil removed from digging the basin. Seriously consider building the wetland using the aquatic safe liner technique instead of hauling in clay. Transporting clay to the work site and then having to haul away permeable soil would make the project very expensive. The reason it costs so much to build a wetland using the compacted clay liner technique is that it takes a long time and requires many pieces of heavy equipment and close supervision to compact the soil that's thick enough to hold water as planned. One should purchase enough clay to form a layer that's 4 foot thick over the entire surface of the wetland being built. This is because the clay delivered by truck is loose and it must be compacted to a final thickness of 2 feet. If you only haul in enough clay to cover the area with a 2 foot thick layer, then the final thickness of the compacted clay would only be 1 foot, which is not adequate. This equation shows how to calculate the volume of clay that's needed to build a wetland that's 60 feet in diameter where clay is not available on site. Now our planned wetland area is 60 foot in diameter. That's equal to 2,831 square feet, and it's equal to 0.06 acres. Now the length of our wetland is 60 feet. The width of our wetland is 60 feet. So to calculate the volume of clay that we need, we're going to take the wetland length of 60 feet, we're going to multiply it times the wetland width of 60 feet, and that's equal to 3,600 square feet. We're going to multiply that times a 4 foot layer of clay, that's equal to 14,400 cubic feet. We're going to divide that by 27 feet cubed per yard cubed, and that will equal 533 cubic yards of clay that will be needed to build that wetland. Now we're going to translate this to weight because oftentimes you order the clay by weight from the supplier, and the clay weight calculation is 533 yards cubed of clay. We're going to multiply that times 1.5 tons per cubic yard. That will equal 800 tons of clay that we'll need to build that wetland. Now what does that mean for dump truck loads of clay? Well, we're going to take that 800 tons of clay and we're going to divide it by 20 tons per dump truck load, and that will equal 40 dump truck loads of clay needed to build this wetland that's 60 feet in diameter. This equation shows how to calculate the volume of clay that we'll need to build a wetland that's 1 acre in size where clay is not available on site. Now our planned wetland area is 1 acre, that's equal to 43,560 square feet, and our diameter would be 208 feet. So our wetland length is 208 feet, our wetland width is 208 feet. To calculate the volume of clay that we'll need, we're going to take the length of 208 feet, multiply it times the width of 208 feet. That's going to equal 43,560 square feet. We then multiply that times 4 foot thick layer of clay, which equals 174,240 cubic feet. We then divide that by 27 feet cubed per yard cubed, and that equals 6,453 cubic yards of clay needed. Now to move that into a weight calculation, we take that 6,453 cubic yards of clay, we'll multiply it times 1.5 tons per cubic yard of clay, and that's equal to 9,679 tons of clay that we need. So the number of dump trucks of clay that we need to be hauled in would be 9,679 tons of clay divided by 20 tons per dump truck load. That's 484 dump truck loads of clay that would be needed to build a 1 acre size wetland. One must identify the source of clay needed for the project. The clay may be obtained from a gravel pit or a quarry, or possibly another wetland you're building that has excess clay. It's of critical importance that you examine and test the percentage of clay at the source before moving it to your site. Another thing you need to consider is what will be done with the permeable soil that's removed from digging the basin for the wetland. Do you need to use dump trucks to move the soil off-site, or can you spread it adjacent to the wetland that you're building? The next step involves hiring someone with an excavator and dump trucks to haul the clay to your construction site. The vegetation and topsoil will need to be removed from the area where the clay will be delivered. This will reduce the chance that permeable material will be mixed in with the clay when it's scooped up for spreading in the wetland basin. One must test for clay content each load of soil that's delivered. It's important to reject loads of soil that are low in clay. The basin for the wetland you're building should be dug before the clay is delivered to the site. The clay that's placed in the basin must be spread in layers from 6 to 8 inches thick, with each layer being compacted. The clay must have ideal moisture content to compact. If it's too dry, you can't compact it. If it's too wet, you're not able to compact it. And there's a simple test that we can use. You just grab a handful of the clay and let's watch and see what happens. Okay, so here's a handful of clay. Look at the dust. That's not a good sign. That means the clay's too dry. And when I grab it and try to form a ball out of it, it just collapses, it falls apart, it fragments. This clay is way too dry. It would be impossible to compact it using any type of heavy equipment. This ball of clay has the perfect moisture content for compaction. My hands are not getting wet as I work it, and there's no dust. Now, if I work it enough, there are a few cracks, but that's okay. We can compact this soil in layers and get it to hold water. This ball of clay has too much moisture for compaction. My hands are slimy and dirty and wet, and actually it has the right moisture content to make a long and thin ribbon, which means it has too much moisture to compact it in layers to form a wetland area. So it needs to be dried before we can compact it. Specialized heavy equipment is needed to compact the soil. One may use a sheep's foot roller, or you can use a vibratory roller, or a wheel loader to compact the clay. It's important to know that the wide tracks on an excavator or a dozer do not compact the soil nearly as well as a sheep's foot roller or a vibratory roller. I would like to show you how we use the compacted clay liner technique to build small vernal pond wetlands on the Wayne National Forest in Ohio. We built 16 wetlands in a riparian area and on a dry ridgetop to help decommission an unauthorized off-highway vehicle trail near the community of Buckthorn, Ohio. Let's watch as we build a wetland on a narrow ridge in a small opening between large oak trees. I used blue-colored plastic ribbons to mark an area for building the wetland that had a change in elevation of 2 feet from the upper to the lower edge. We completed the project in early winter when the soil was moist. We only had an excavator used for construction. Fortunately, John Utterback operated the excavator. He and I have worked together for 25 years to build over 1,000 wetlands across Kentucky, Ohio, and New York. John began construction by using the bucket and thumb attachment of the excavator to remove small diameter trees from within the area marked by blue ribbons. He placed these trees along the edge for later placement in the finished wetlands. Next, we dug a test hole near the center of the work area to see if there would be enough clay to build the wetland. We found a layer of clay on the surface that was 4 feet thick. This would work well for building a wetland. You're looking at a test hole we dug the day before, and this was in an adjacent area where there was too much rock and not enough clay to build a wetland. The next step was to remove the topsoil from the surface of the ground. The topsoil was placed in piles along the edge of the work area where it would be later returned to the finished wetland. The topsoil is dark colored and contains fine roots. The excavator removes leaves, shrubs, and topsoil to a depth of 10 inches to expose the light brown colored clay soil. The main reason the topsoil is being removed is that the material can't be compacted to hold water in the wetland that's being built. The process continues until all the topsoil is removed from the work area. The next step involves digging down vertically about 3 feet deep along the entire outer edge of the wetland that we're building. The teeth on the bucket of the excavator are used to cut through the topsoil and the roots. Organic soil and large diameter roots are removed and placed in a pile. Clay texture soil that is removed is placed in another pile. Now the excavator picks up a bucket of clay and places this clay in the base of the corner that was dug out along the edge. The bucket is used to compact the clay soil to form a wedge in the corner. The back of the bucket is used to compact the clay. Large roots are removed that are mixed in with the clay. Additional buckets of clay are added and spread in layers about 6 inches thick. The excavator builds a section of groundwater dam along the perimeter that's within its reach. The shallow groundwater dam will reduce water leaking out of the wetland through the topsoil and the roots around the water's edge. This drawing shows how we're building a small wetland that will be 12 inches deep in the center. A groundwater dam that is 3 foot deep is built around the entire perimeter of the wetland. This will give us a thick layer of compacted clay along the shoreline that won't leak. The entire basin will be lined with clay that is compacted in layers to be at least 24 inches thick. Topsoil will then be placed over the compacted clay. John continues adding buckets of clay along the outer edge of the wetland being built. The clay is shifted and shaped to form a wedge along the outside perimeter of the wetland being built. Each layer of clay is compacted using the bucket of the excavator. The clay is placed high enough to match the elevation of undisturbed ground along the outer edge of the wetland being built. The clay soil is mixed before it's placed and compacted. The process of building this clay wedge or groundwater dam takes time. However, if you were to skip this step, the wetland would only contain water a few days out of the year. The compacted clay is built up until it's equal in elevation to the surface of the adjacent undisturbed ground. John continues to add clay and to compact this clay in layers to form an above-ground dam along the lower edge of the wetland being built. John moves the excavator so the machine is positioned on top of the dam he just built. He removes soil from the upper edge of the wetland being built and places this soil on the downhill side of the dam. This soil will be spread to form a gradual back slope on the dam. The soil is also being removed from the center and upper edge of the work area to form a basin for the new wetland. This drawing shows where we're building the wetland. The surface of the ground is sloped. There's a 2-foot change in elevation from the upper to the lower edge of where we want to build the wetland. Here you see how much soil we need to remove to build the wetland that's colored in blue. We will need to remove quite a bit of soil from the upper edge so we won't have a vertical drop-off leading down into the wetland. The center of the wetland must be dug 4.5 feet deep to build a wetland that will be only 1 foot deep in the middle when we're finished. This is because there's a 2-foot change in elevation from the upper to the lower edge of the wetland we want to build. We want the finished wetland to be 1 foot deep in the middle. We'll need to dig 2 foot deeper to make room for placing 2 feet of compacted clay. And we need to allow space for spreading 6 inches of topsoil in the basin. We continue to remove soil from within the wetland being built to create a basin that is deepest in the middle. The basin is dug 4.5 feet deep in the middle, so we may add 2 feet of compacted soil and 6 inches of topsoil to produce a wetland that is 1 foot deep in the middle. After soil has been removed from the center and uphill edge of the wetland being built, the excavator operator continues digging the trench with a vertical wall around the marked perimeter. Clay is placed in the cutout corner. This soil is placed to form a wedge, then is compacted using the bucket of the excavator. The moisture content in the clay is ideal for compaction as it's not too wet or too dry. The groundwater dam is eventually built around the entire outer edge of the wetland. Now that the groundwater dam has been built, the soil is shaped to form a basin that does not have high mounds or dips. We want to make sure that there will be at least 24 inches of compacted clay in the wetland basin when it's completed. John begins compacting the soil in the basin using the excavator. We call this track packing or walking in the clay. John is careful to track pack all the soil in the wetland basin. He moves the excavator from left to right and watches to make sure that he runs over each area of his soil at least 5 times and does not leave ridges of uncompacted soil. While the vibratory roller would have done a better job compacting the soil, we did not have the budget to bring in another piece of heavy equipment. John changes direction and travels over the soil in the opposite way to obtain even more compaction in the wetland basin. The vibration and the heavy weight of the excavator rearranges the soil particles and collapses voids in the ground. Here's a close-up view of the wetland basin that has been compacted using the tracks and weight of the excavator. One can tell that the soil is compacted because there are no sharp ridges or drop-offs along the edge of the excavator track marks, and because we were not able to make deep divots using the heels of our boots. John Utterback uses a laser level and a receiver to check elevations along the length and width of the spillway being made for the new wetland. John places the topsoil and the organic material that was saved in the wetland that we've lined with clay that's been compacted in layers to a total thickness of 24 inches. The topsoil and organic material are not spread evenly, but they're placed in naturally appearing ridges and mounds. He removes the piled soil along the upper edge so that runoff can enter the finished wetland. The rough and loosen technique is not used to loosen compacted clay in the basin, as this would create pathways for water to soak into the ground, and the wetland would not hold water. John starts by placing topsoil in the center of the wetland and works his way out backwards, removing track marks and loosening topsoil that he has run over. John makes sure to taper the soil around the edges of the basin so the wetland will appear natural. The large woody debris that was piled along the edge of the work area is placed in and around the wetland at the same time topsoil is being spread in the wetland. The excavator operator places the wood that is within reach of the machine at the same time the topsoil is being spread. This way he won't have to return and damage the work that's been already done. It is very important that you stay in front of the excavator and communicate with the operator as they work their way out backwards. This way they won't have to return to fix something that you don't like. 3 things are happening in this video. John is placing woody debris where topsoil and organics have been spread. He's shaping and sloping the soil on the backside of the dam, and he's using the rough and loosen technique to remove heavy equipment track marks and to prepare soil on the backside of the dam for seeding and planting. Here's how the vernal pond wetland appears within minutes of the excavator moving uphill to build the next site. The wetland basin is 12 inches deep in the middle and contains 24 inches of compacted clay. Topsoil, organics, and large woody debris have been spread within and around the wetland basin. The access road leading to the new wetland is being decommissioned by filling in gullies, using the rough and loosen technique, and by adding pit and mound topography, and finally by placing many large trees that make OHV traffic impossible. We built a total of 16 vernal pond wetlands within the access road as part of the restoration program, and this was done to control erosion and to improve habitat for a diversity of wildlife species. Let's look at how the compacted clay liner technique was used to restore Blue Lake near the community of Ruidoso on the Lincoln National Forest in New Mexico. Blue Lake is a naturally formed, isolated, ephemeral wetland. It occurs at high elevation, 8,081 feet, and it's in a basin that doesn't have a stream entering or leaving it. Ponderosa pine trees surround Blue Lake, which was largely a dry meadow containing grasses and occasional patch of sedge. This region receives less than 20 inches of precipitation each year. Blue Lake was dry and it rarely held water. Sometime before 1994, 2 large ponds were dug near the center of Blue Lake, most likely to provide water for livestock. The constructed ponds would only hold water for very short periods of time, even though they were dug 5 feet deep. In 1994, the 2 constructed ponds within Blue Lake were made larger and deeper by the Forest Service using 2 dozers. The deeply dug ponds failed to hold water. The Forest Service mixed large quantities of bentonite into the pond basins to make them hold water longer. It didn't work. Bentonite is sold in 50-pound bags. The fact that spreading bentonite failed to seal the leaky ponds should be no surprise. I've tried many times over the years to repair leaks in ponds and wetlands with bentonite and bentonite mats with no success. Get on the internet and you'll find all sorts of websites showing how people are spreading and mixing bentonite in pond basins to make them hold water. Bentonite is an absorbent swelling clay consisting mostly of montmorillonite, which can either be sodium montmorillonite or calcium montmorillonite. Sodium montmorillonite has considerably greater swelling capacity than calcium montmorillonite. You may not know this, but bentonite is the primary ingredient in kitty litter. Here's a sample of bentonite that I took out of a bag. I grab a handful of it. I try to compact it. It's too dry for compaction. We need to add water. I'm adding water to the sample of bentonite, and then I'm going to mix it. And I want to get it the right consistency for compaction, where I can form that ball, but yet my hands are not wet. So right here, I have the perfect moisture content for compaction. Let's see how it works. Notice that when I work this bentonite, it shatters, it cracks, it fragments. It's just not going to work. You're not able to compact this because it's not clay. It's different than clay. I'm going to keep adding water to this sample of bentonite and find out how long of a thin ribbon I can make. It takes a long time to work water into bentonite. And this is something to remember on a wetland project. If you want to use bentonite, it's very difficult to mix water in this with because it's very sticky. It will stick to all your equipment, and it takes forever to get that water mixed in. So here I've been mixing the water in and mixing the water in. I'm going to try to make a ribbon out of it, and what's happening is that it's breaking on me. The reason it's breaking is it has low clay content. In fact, this soil sample is acting a lot like a sandy loam, only with a fine gravel in it. So I don't know how people think that throwing this into a wetland dry and working in a disc would help the wetland hold water. The only sure way to get your wetland to hold water is to add layers of clay and to compact each layer of clay until you reach 24 inches total in thickness. For some unknown reason, people believe that bentonite works like pixie dust to repair a wetland or a pond that doesn't hold water. Another problem with using bentonite is that it is not aquatic safe. The bucket on the right contains water from a wetland along with the larvae of healthy frogs. The water in the bucket on the left was taken from the same wetland, only I placed a small piece of bentonite mat in it the day before. The bentonite went into solution and quickly killed the tadpoles. I've met hundreds of people across North America who have tried using bentonite to fix their leaking ponds. Some have spent as much as $30,000 to purchase and apply bentonite into the soil of a leaky pond. None of these projects have been successful. The most effective way to seal a leaking wetland is to line the entire basin with soil that's high in clay. Compact each layer of clay until the total thickness of the compacted clay is 24 inches or more. There are no shortcuts. After they found out the bentonite didn't work, the Forest Service erected a fence around Blue Lake to keep the livestock out. It is very possible that controlling livestock access to Blue Lake changed how long it held water. The livestock were compacting soil on the surface. Once the livestock were removed, the thin layer of compacted soil loosened due to freezing, thawing, and root action, thereby shortening the hydro period of Blue Lake and the deeply dug ponds. I visited Blue Lake for the first time on August 24, 2010, with Brian Davis and Larry Cordova. We used a 48-inch long soil auger to determine that an average of 4 inches of topsoil was found on the surface of Blue Lake, and there was at least 3.5 feet of clay beneath. The ribbon test showed that the clay content in the soil of Blue Lake was very high. This was evidenced by this 4-inch long thin ribbon. The clay was black in color and may have been deposited by volcanic action. The clay was of superior quality compared to the bentonite that is often spread in leaking ponds. I returned in 2023 to dig deep soil test holes in Blue Lake using a backhoe. The deep test holes we dug in the undisturbed areas of Blue Lake contained a layer of clay on the surface about 4 foot deep, with dry sand beneath the clay. We also dug deep test holes in the bottom of the deep ponds that had been dug. The deep test holes we dug in the bottom of the 2 ponds showed that coarse texture soil containing sand and rock was only about 12 inches below the surface. Most of the clay overlaying the sand and rock had been removed to dig the deep ponds. This photo shows that the clay is black in color and the sand is brown or orange. The main reason Blue Lake was not holding water was that rainfall and snowmelt were flowing into the 2 ponds and then soaking into the sand beneath the ponds. The deep ponds were injecting water into the ground. The sand that we found beneath the clay in the deep dug ponds at Blue Lake was draining the wetland a whole lot like the hole in the bottom of a flower pot. When the water pressure increased after a rainfall, that water just leaked out of that hole. A design was prepared for restoring Blue Lake that focused on controlling the leaks in the 2 ponds. The ponds would be reshaped and combined to appear more like a natural wetland, with a maximum water depth of 5 feet. It was not necessary or possible to construct a groundwater dam to prevent water from leaving Blue Lake. This is because Blue Lake is in a basin with sand underlaying the clay. We plan to build additional small wetlands within and near Blue Lake to provide breeding habitat for amphibians and for crustaceans. These would be built using the same compacted clay liner technique as for the larger wetland, only they would be much shallower, from only 12 to 18 inches deep. The Forest Service contracted with a local business to provide a backhoe with an operator and a dozer with an operator to complete the project. Since this project was completed, I now recommend using an excavator and a dozer and a vibratory roller to complete similar projects in the future. The backhoe begins work by removing the topsoil within and surrounding the constructed ponds. It was necessary to remove the topsoil and the plant roots because we would need to harvest about 12 inches of clay from the area around the ponds so we could line the bottom of the ponds with clay. The grasses, roots, and topsoil were placed in piles along the edge of Blue Lake for later placement in and around the finished wetland. We hoped that the topsoil would contain viable cysts of fairy shrimp and tadpole shrimp that had not been seen in Blue Lake for years. The dozer operator also worked to remove topsoil from where the clay would be obtained. Pink-colored plastic ribbons were tied to plants to show the heavy equipment operators where plants and topsoil should be removed. The plants and topsoil were removed at the same time and placed in piles beyond the area marked for construction. After the topsoil was removed, the dozer operator worked to remove and pile the clay needed to cover the sand in the bottom of the ponds. The dozer is having difficulty removing a layer of clay because the soil is so hard and dry. The operator must shift most of the weight of the machine onto the blade to try to get it to cut into the ground. The backhoe was not able to remove the hard clay. It was necessary to use the ripper attachment on the dozer to loosen the top layer of clay so it could be pushed and piled for use in lining the basins of the wetlands we were building. The dozer has the power to pull the ripper attachment through the dry and hardened clay. The dozer and ripper do a much better job loosening the compacted clay compared to using a disc or a plow on a tractor. We watched closely the surface of the ground behind the dozer for sand and would then inform the operator when sand was observed so that he could move to another area where the clay was thicker to loosen it with a ripper. The dozer is now able to easily scrape off the top layer of clay and push it into piles where it could be mixed with water before it's spread and compacted. We found it to be much more efficient to create numerous smaller piles around the work area instead of making one or two large piles. You can tell that the dozer is pushing soil that's high in clay because of the large unbroken clumps and the shine on the smooth and compacted surface of the clay that was cut by the dozer blade. One can also see the brown-colored sand in the basin, and this shows us that the dozer should not dig any deeper to remove clay. The dark-colored clay is now being spread and compacted over the light-colored sand. Here we're removing the sand so we can make the wetland deeper. The sand will then be covered with compacted clay that is 24 inches deep. The backhoe operator picks up the sand and moves it away from the wetland being built. The sand can be placed in higher ground in sunlit areas to create turtle nesting mounds. The clay was too dry to place in the wetland and compact. Water was needed to mix with the clay to obtain optimum moisture for compaction. The Forest Service provided a large engine containing water for fire suppression that we used to moisten the clay. We decided that both water and time would be conserved by moistening piles of clay instead of spraying the entire construction area. The humidity was so low and the winds were so high that evaporation was a major concern. Here the backhoe is mixing clay and water. The backhoe operator used the front bucket on the machine to mix water into the clay. This process took time because the backhoe did not have the power needed to lift and mix the large quantities of soil like what could have been done using an excavator. You may need to add water to moisten clay soil for compaction anywhere in North America. Here we're adding water to dry clay so we can compact it to build a wetland at Sweetbriar College in the state of Virginia. We were not able to moisten piles of clay too far in advance because of the low humidity and rapid evaporation. We were unable to compact the clay if it dried out. We also had to be careful where to drive and to park the heavy firefighting engine with its large water tank so it wouldn't get stuck. Once the clay is mixed with water to the optimum moisture content, the backhoe operator scoops up moistened clay and then spreads the soil in a 6-inch thick layer. He then levels the soil so there are no ridges, making it easier to compact. The backhoe operator compacts the clay layer by traveling over it many times. The operator moves the machine from left to right and then from right to left to compact even the ridges between the tire ruts. The backhoe carries around the front bucket filled with soil for extra weight to aid with compaction. At the same time, the dozer operator is spreading a layer of soil that the backhoe will soon be compacting. The wooden stake you see is one of many that were placed to show the heavy equipment operators where the compacted clay is 24 inches thick. We are constantly using the optical level and the grade rod to monitor the thickness of the compacted clay in each area. It is of critical importance that all who are on site are systematic in how the clay is spread and compacted each day. The stakes are placed, maintained, and moved when needed to show the operators which unit of ground to work on each day. The backhoe was used to compact each layer of clay that was spread in the basin. The rubber tires on the backhoe did a much better job compacting the soil compared to using the tracks on the dozer. Notice how the backhoe is carrying a load of clay in its front bucket. The added weight helps to increase compaction. We compared the amount of compaction obtained by using the hand-operated vibrating plate compactor with that of the tires on the backhoe. We found that the backhoe was much faster and did just as good a job compacting the soil. Here the backhoe is placing and spreading a layer of moistened clay along the edge of the wetland being built. It's very important that 2 feet of compacted clay is present beneath the shoreline of the wetland where the water will be shallow as well as in the deeper parts of the basin. I suggest cutting a bench with a 2-foot-high vertical face around the outer edge of the wetland being built, and then filling this bench with a wedge of clay that's compacted in layers like what the backhoe is doing here. This ensures that the shallow water along the shoreline of the new wetland also be based on 2 foot of compacted clay. Notice that the construction level is set up on a tripod in the background. We are regularly taking elevations to measure the thickness of the compacted layers of clay. We continually measured the thickness of the compacted clay layer by using a grade rod and a construction level. We then let the heavy equipment operators know how many more layers of clay were needed to reach the total thickness of 24 inches. The dozer operator works ahead of the backhoe to spread and level the next layer of clay. The blade and tracks on the dozer level clumps of soil and fill in ruts so the backhoe can do a complete job of compacting each layer of soil. The tracks on the dozer provide some compaction. It's best to build the wetland with a simple round or oval shape and a level bottom when using the compacted clay liner technique. This is because it's almost impossible to compact clay in dips and over ridges or around points and peninsulas. One can easily add ridges, islands, mounds, peninsulas, and shallow water bays by placing topsoil in the basin that's lined with compacted clay. I now use a penetrometer to measure soil compaction. The penetrometer is a scale that lets you know the degree of compaction in pounds per square inch. Here John Utterback is using a penetrometer to measure soil compaction in a large wetland that he's building at a different site. We want the dial on the penetrometer to read 300 pounds per square inch from the surface down to 24 inches below the surface. We've almost finished lining the wetland basin with compacted clay that's at least 24 inches thick. There should be no piles of clay left over, providing the soil that was spread in the wetland has been compacted. The dozer begins spreading topsoil over an area of compacted clay while the backhoe operator continues to place and compact clay soil in the basin. Notice how the compacted clay is smooth while the spread topsoil is rough. It doesn't take long for the dozer to spread topsoil that was saved. The dozer excels at pushing and spreading soil distances less than 300 feet. The operator shows skill in scraping off the topsoil and not scuffing the grass that's beneath. The backhoe operator scoops up topsoil and spreads it in places that are further away from the piled topsoil the dozer is moving. The operator moves backwards as it spreads the topsoil to avoid compacting the topsoil with his rubber tires. The dozer operator is asked to travel over the topsoil a minimum number of times to avoid compaction that may hinder plant growth. The topsoil is spread rough with clumps to increase plant diversity. The backhoe operator places a log in the finished wetland to provide waterfowl with loafing sites and birds with perches. The front bucket is called a clamshell bucket that allows the backhoe operator to pick up and carry logs. Native species of plants are seeded in and around the completed wetland. Here's how Blue Lake appeared soon after construction. Rain that fell in the summer of 2013 began filling the wetlands. This photo was taken as the large wetland within Blue Lake was filling on August 29, 2013. This photo shows one of the smaller wetlands that was built in Blue Lake at the same time. Western spadefoots are now breeding in the restored wetland. Here's one of many western spadefoot metamorphs found in the restored Blue Lake. I'm happy to report that fairy shrimp are again breeding in the restored wetlands. And most excitingly, tadpole shrimp are breeding in the restored wetlands. Here's how the restored Blue Lake appeared in 2022 after a forest fire killed the surrounding pine trees. This Google Earth image shows how Blue Lake appeared in 2024. The dark areas are water and the gray areas are saturated soil. You'll now find a diversity of native sedges and rushes in the restored wetlands. The wetlands now contain water long enough to be used by waterfowl along with a diversity of amphibians and invertebrates for breeding. Robin Anchild began building large wetlands in 2016 near the confluence of Cherry Creek and the Kootenay River in British Columbia, Canada, and she was using the compacted clay liner technique. You can see the emergent, wet meadow, and the ephemeral wetlands she has restored on land owned and managed by the Nature Trust in British Columbia on this aerial photo taken on June 1st, 2023. Robin supervised 2 excavators, 1 wheel loader, and a dozer as they began construction by removing and piling the vegetation and the topsoil along the outer edges of the work area. Here the dozer and the wheel loader push topsoil and vegetation to the edge of the work area where the excavator picks it up and piles it outside of the wetland being built. The vegetation and the topsoil were first loosened by using the excavator. The dozer operator is removing vegetation and topsoil from the work area, while the excavator operators continue to pile vegetation. The wheel loader operator does not appear to be contributing to the project at this time and should probably be given instructions on what to do. This is why it's important to be on site managing the construction of the wetlands. The dozer operator is using the corner of the blade to loosen clay on the surface so it can be more easily moved by pushing it with the dozer. The clay will then be piled and later used to line the excavated basin. This image taken by a drone shows the worksite after vegetation and topsoil have been removed, but before the wetland basin has been excavated. The orange-colored excavator is digging a trench across the work area to serve as a guide in the excavation of the wetland basin. The bottom of the trench is dug to follow the contours of the wetland basin that's being excavated. However, the trench is being dug deeper to allow for clay that will be returned and compacted in layers. The excavator is digging a second trench that is perpendicular to the first trench that was dug. Think of this trench like what you would do to cut a pie into 4 equal pieces. These trenches will serve as a guide to the excavator operator as it removes each large piece of soil. The excavator operator is digging the basin while using the bottom of the trench as a guide to the maximum depth of the wetland that's being built. The excavator places the soil that's high in clay in one pile and the soil that's low in clay in another pile. The wheel loader moves the piled soil out of the wetland being built. Here the dozer operator is removing clay near the surface. The machine will then dig out deeper permeable soil to form a basin where clay will later be returned and compacted in layers. The dozer and the excavators are finishing the excavation of the wetland basin so it will be ready for placing and compacting the clay. The wheel loader has begun compacting a layer of clay that was spread over a shaped section of the basin. We watch as the wheel loader operator drives back and forth to compact a layer of clay in the wetland basin. The ground pressure of the wheel loader is high because of the machine's weight and its rubber tires. The wheel loader is capable of compacting soil over a large area in a very little amount of time. The operator of the wheel loader works to stay out of the ruts and to drive over the ridges between the ruts to compact the soil. The dozer is used to periodically level the surface of the ground so the wheel loader can effectively compact the soil in the wetland basin. Watch as the tires on the wheel loader spin in the mud. Even though this wheel loader has 4-wheel drive, it's not efficient at compacting mud or wet soil. We're looking at the wheel loader that's stuck in the wet soil. The main purpose of the wheel loader with its rubber tires is to compact the clay. This is why most of the heavy equipment that's used to build wetlands is on tracks, not on wheels. The topsoil and vegetation that were saved have now been spread over the compacted clay in the wetland basin. The excavator operator is placing large woody debris in the finished wetland. The western painted turtle will use the logs for basking, and ducks will use the logs for loafing. Sometimes we can't help but rearrange the logs by hand to create places for animals to hide. The excavator in the background is doing the final shaping of the wetland. Topsoil that was spread by the dozer over the compacted clay is being rearranged into shallow pits and mounds, and the tracks left by the heavy equipment are being swept and loosened. The laser level is also being used to measure the final depth of water in the wetland. Here's how 3 of the new wetlands appear the following spring. A diversity of plants are growing in the wetlands 2 years after construction. The wetlands were built to have different depths, shapes, and slopes. This wetland has shallow water emergent and wet meadow components. Some of the wetlands that were built will dry in late summer. However, they can all contain water all year when filled in late spring by floodwater from the Kootenay River. This aerial photo shows how some of the wetlands appeared on June 1st, 2023. The wetlands were restored with natural shapes and various depths. They're also hydrologically connected with floodwater from the Kootenay River. The wetlands were built without dams, without water control structures, pumps, or diversions that all require maintenance. Our last visit will be to Round Hill Farm in Kentucky. We're going to be building a 1-acre wetland to provide habitat for the sandhill crane and a diversity of animal and plant species. The site we chose for building the wetland is on top of Round Hill. It's an old corn and pasture field that's well drained. We wanted to build the wetland in an area surrounded by fields where the sandhill crane would feel safe during migration and hopefully nest in the future. We set up a laser level in the center of the area where we wanted to build the wetland, and we used a dual-sided grade rod to identify a large and level area for building the wetland. Our plan was to build a wetland that was less than 12 inches deep in the center and shaped like a huge satellite dish. I tied orange-colored plastic flagging on the tall grasses to mark the perimeter of the wetland that could be built in an area with less than a 2-foot change in elevation from the upper to the lower edge. John Otterback used his excavator to dig a deep test hole in the center of the area that we marked for building the wetland. We found that the topsoil layer was 8 inches thick with clay loam extending down 5 feet below the topsoil. I could make a thin ribbon that was 2 inches long from the clay loam texture soil. We found sandy loam soil beneath the clay loam. We were not able to dig down to bedrock, and no groundwater entered the hole. We decided to use the compacted clay liner technique to build the wetland because it was not possible to build a groundwater dam, and no groundwater entered our test hole, and the layer of clay near the surface was at least 4 feet thick. If we simply dug a depression for the wetland without lining the basin with compacted clay, the wetland would only contain water a few days out of the year, and the soil would go dry. We searched the area where the wetland would be built for milkweed because we wanted to protect these plants that are used by the monarch butterfly and other pollinators. No milkweed was found growing on the site. This is butterfly milkweed, a most attractive wildflower. We found this growing near the center of another wetland we built on the Round Hill Farm. We tied orange flagging around the plant to mark its location so it wouldn't be affected by mowing. Here John Otterback is digging up the butterfly milkweed so it could be planted at a portion of the field that would not be disturbed by the construction of the wetland. The bucket on the excavator is large enough so the milkweed and all of its roots can be moved. The first step in construction of the sandhill crane wetland is to remove and to save the topsoil for later spreading in and around the completed wetland. John uses his Case 1150G dozer to remove the plants and the topsoil. The material he removed contained plants, roots, and organic soil that were not able to compact to hold water. The dozer digs a basin for the wetland that's 3 foot deep in the center and shaped like a large satellite dish. We're digging the basin 2 foot deeper in the center than the planned 1 foot final depth of the wetland because we need to cover the bottom of the wetland with 24 inches of clay that's compacted in layers. John removes a large amount of soil to transform this hill with a convex shape into a wetland with a concave shape. He separates the clay and the reddish-colored sand and the darker-colored topsoil as removing the soil to make the basin. He places and saves the clay in one long pile, we call this a windrow, and then spreads sandy soil outside of the area where the wetland's being built. John uses the dozer to remove clay from the basin of the wetland that's being built. The topsoil has been placed in a windrow along the right side of the wetland being built, and with the clay being piled on the left side. Here John is taking an elevation reading with the laser to see how much deeper he needs to dig the basin for the wetland. Unfortunately, I don't have many photos showing us taking elevations, but assure you we've done this a lot. It's of critical importance that you take elevation readings often to check the depth of the wetland being built and to see if the layer of compacted clay in the basin is at least 24 inches thick. Using a dozer to dig the basin for a wetland is much faster and cheaper than using an excavator with a dump truck to move the soil off-site. The dozer is very efficient at moving soil distances up to 400 feet. This is a large and heavy sheep's foot roller that we use to compact clay that is spread in the wetland basin. John Otterback uses his large, antique, 105 horsepower Oliver tractor to pull the sheep's foot roller. The heavy weight of the tractor and his rubber tires also help in compacting the soil. I found that there's no better way to compact the soil in this wetland basin than to use this large tractor and the sheep's foot roller. This gives you an idea how fast the tractor moves when pulling the sheep's foot roller. John travels in circles and he moves from right to left to compact each layer of soil by traveling over the surface 5 or 6 times. John is very systematic about how he places clay and how he compacts this clay in the wetland being built. He uses wooden stakes to mark cells on the ground that are 50 feet wide. He then works to place and compact layers of clay within each cell instead of trying to spread clay over the entire basin. There are many reasons for doing this. It's going to take days to build the wetland, so he can better keep track of the thickness of the clay if the basin is divided into cells. And the other is that when it rains, he won't have a muddy mess where it's not possible to add or to compact the clay. Here's how the basin appears when layers of clay are being added and compacted. The topsoil that was saved is piled along the outer edge of the wetland being built. The dozer is used to spread layers of clay, and the tractor and the sheep's foot roller are compacting each layer. John continues to compact the soil until he sees there's no more ridges left and that the feet of the sheep's foot roller are no longer punching into the ground. John is using the penetrometer to measure the degree of compaction of the clay in the basin. He finds that the clay has been compacted to 300 pounds per square inch from the surface down to 24 inches below the surface. He walks around the basin and takes numerous measurements to make sure there are no places where the soil is not compacted. Here's how the surface of the ground appears when it's been compacted. You can see that the squares left by the sheep's foot roller pushed into the soil are barely visible. If these squares were punched in 3 to 4 inches below the surface, it would be necessary to continue compacting the soil. We have now built a basin that's 1 acre in size and 12 inches deep in the center on top of a hill. The basin has gradual slopes and is lined with clay that's been compacted in layers up to a thickness of 2 feet or more. It's time to spread the topsoil, so John uses the dozer to begin pushing the soil into the basin of compacted clay. John backs up behind a pile of the topsoil and pushes a bladeful across the wetland basin. He's careful not to dig into the compacted clay soil. We're not concerned with spreading an even layer of topsoil, so you're going to find areas where the topsoil is spread thicker and other areas where it's spread thinner. Here's how the completed wetland basin appears after one heavy rain. You can see the rough and loose surface of the topsoil, and there's lots of small puddles. The rough and loose surface of the soil will provide conditions for a diversity of plants to grow in and around the wetland. Here's how a wetland appears at the Round Hill farm that was built using the compacted clay technique 1 year after construction. The restored wetlands are being used by Canada geese and by waterfowl. Sandhill cranes are using the new wetlands for feeding. Many sandhill cranes are stopping by at night to rest and to feed during migration. We observed a roseate spoonbill using the new wetlands in July of 2023. The roseate spoonbill is rarely seen in Kentucky, and the observation attracted much attention from birders and from the media. In summary, one may use the compacted clay liner technique to build wetlands where it is not possible to build a groundwater dam, and where groundwater is not near the surface, and where there is at least 4 foot of clay near the surface of the ground. Here are some photos showing wetlands built using compacted clay liner technique. This is a perennial water emergent wetland that we built at McBrayer Elementary School in eastern Kentucky. It's 19 years old. This vernal pond ephemeral wetland was built at McBrayer Elementary School in Moorhead, Kentucky, also 19 years ago. This small vernal pond wetland was built on the Danube National Forest in Kentucky 17 years ago. Here's a wetland we built 20 years ago at the Southwestern Research Station near Portal, Arizona. Here's one of 114 wetlands built by hand using the compacted clay liner technique at the Fort Ancient Earthworks and Nature Preserve in Oregonia, Ohio, over 2,000 years ago. We built this wetland on a ridge within the Danube National Forest 20 years ago. This wetland was built in a mined area within the Danube National Forest 18 years ago. Here's one of several wetlands we built using the compacted clay liner technique at Sweetbriar College in Virginia 15 years ago. Building a wetland using the compacted clay liner technique, it's a lot like putting together a puzzle with over 1,000 pieces. It requires great attention to detail and lots of patience, but when you've finished, you're likely to have a masterpiece. This is Tom Biebighauser. I'm with Wetland Restoration and Training. I invite you to subscribe to this video series on how to build a wetland, and we look forward to seeing you in the next episode.